The Belchen Tunnel, located in Switzerland and part of the A2 motorway, is an essential transit route that is over 50 years old. Due to its age and structural wear, the tunnel requires a complete renovation. To avoid traffic chaos during the renovation, a replacement tunnel is being built parallel to the existing structure. This project, led by Marty, presents a unique challenge as the surrounding rock consists partially of gypsum cupar, which expands significantly when in contact with water. Marty's solution to this challenge was to deploy a tunnel boring machine, TBM, along with specialized construction equipment developed through years of experience. This approach enables the team to manage the complexities of the Belchen Tunnel's geology effectively. The TBM is a critical piece of equipment in the excavation process. Equipped with a 14-meter cutting head, the machine advances through the mountain, boring through the rock. The cutting head is fitted with rollers, which are designed to break off rock fragments as the machine moves forward. The number and arrangement of these rollers are optimized specifically for the geological conditions of the Belchen Tunnel, with particular consideration for the gypsum cupar. As the TBM advances, it injects stabilizing materials into the rock through injection ports located directly behind the cutting head. These materials help reinforce the tunnel walls and prevent any collapse. The machine is also equipped with a hydraulic system capable of exerting up to 2,000 tons of pressure, which pushes the TBM forward while simultaneously supporting the already excavated sections of the tunnel. Every 2 meters, the TBM stops to allow for the installation of tunnel segments. These segments, known as tubings, form the tunnel's initial lining and are crucial for securing the excavation site. Each segment is made from high-strength steel fiber reinforced concrete, produced at Marty's on-site manufacturing plant. This concrete is hardened in a 55 degrees Celsius kiln to ensure it meets the necessary durability standards. The installation of the tubing segments is a highly coordinated process. Each tunnel ring consists of 7 segments, which are fitted together under pressure within the shielded environment provided by the TBM. These rings create a sealed structure immediately behind the TBM, ensuring that the tunnel is secured as it advances. As the TBM advances, the rock debris must be continuously transported out of the tunnel to avoid delays. Once the initial tunnel lining is complete, Marty begins the installation of a secondary lining. This process begins with the application of a waterproof membrane, which is attached to the tunnel walls using heat. Sheets of plastic are applied and welded together using hot air, forming a continuous barrier that prevents water from seeping into the tunnel. Each weld is pressure tested to ensure there are no leaks. With the waterproofing complete, Marty proceeds to pour the concrete for the tunnel floor. This step requires careful coordination as construction vehicles must continue to access the TBM while the concrete is being poured. To manage this, a mobile concrete formwork system is used, which is mounted on a bridge structure above the tunnel floor. The formwork can be moved as needed, allowing for continuous concrete pouring without disrupting traffic to and from the TBM. The concrete for the floor is poured in 10-meter sections, with the formwork advancing each day as the previous section hardens. Marty's mobile concrete plant, located on site, supplies the concrete, ensuring that construction progresses smoothly without delays. In parallel, steel reinforcement cages are installed along the tunnel walls in preparation for the next concrete phase. These reinforcement cages, which weigh several tons, are hoisted into place using specialized equipment. Once the reinforcement is in position, the walls are poured with high-strength concrete. This process is repeated section by section, gradually completing the tunnel's structural framework. After the tunnel's floor and walls are finished, attention shifts to the arch. Like the walls and floor, the arch must be waterproofed before the concrete is poured. Sheets of waterproof membrane are attached to the arch using the same hot air welding technique used for the walls. Once waterproofing is complete, Marty installs the reinforcement cages for the arch. This work is performed using a system of mobile work platforms, which provide workers with access to the entire surface of the arch. These platforms allow for precise placement of the reinforcement, ensuring that the arch will be strong enough to support the tunnel's final load-bearing capacity. The arch concrete is poured in a similar manner to the walls and floor, with formwork advancing in 10-meter sections. Special care is taken to prevent the concrete from hardening too quickly, which could lead to cracking. To address this, Marty uses an insulation system that regulates the concrete's temperature, allowing it to cure evenly. Completion of the tunnel structure. With the floor, walls, and arch in place, the primary structure of the tunnel is complete. The final step in the construction process is the installation of the intermediate ceiling, which separates the traffic lanes from the service and ventilation areas above. This ceiling is built using the same mobile formwork system that was used for the tunnel floor. Once the ceiling is in place, Marty focuses on the remaining finishing touches, including the installation of electrical systems, lighting, and ventilation ducts. The completed tunnel will be fully equipped to handle modern traffic demands, with state-of-the-art safety systems in place to ensure smooth operation. The Belchen Tunnel project is a showcase of modern engineering and construction techniques. The difficult geological conditions, particularly the presence of gypsum cupor, required innovative solutions to prevent structural damage. Marty's specialized equipment, including the TBM and mobile formwork systems, was critical in overcoming these challenges. The project also highlights the importance of precise planning and coordination. Every aspect of the construction process, from the excavation to the final concrete pours, had to be carefully timed to ensure the project stayed on schedule. Marty's in-house development of equipment and control systems allowed the team to adapt quickly to the project's unique demands. The construction of the Belchen Tunnel replacement represents a significant achievement in Swiss infrastructure development. By utilizing advanced tunneling technologies and specialized construction techniques, Marty has successfully navigated the challenges of working with difficult geological conditions. The project's success will ensure that the A2 motorway continues to serve as a vital transportation route for decades to come. With the completion of the new tunnel, work will soon begin on renovating the original Belchen Tunnel, further enhancing Switzerland's road network and improving safety for all motorists. The routeway refers to the entire system within the tunnel that facilitates train operation, including components like the track, cable management systems, communications, signaling, and mechanical systems such as fire mains, drainage, and walkways. As the routeway is now complete, it's fascinating to look back at the process that brought the project to this point. One of the first tasks was drilling around 250,000 holes into the tunnel lining to support the infrastructure. This massive undertaking was handled by drilling rigs that moved throughout the tunnel. Once the holes were drilled, the team installed the cable management systems. These are trays that surround the tunnel lining and support 15,000 kilometers of cables, including those for lighting, low-voltage power, and other essential systems. The next major task involved installing the track. Thousands of sleepers had to be positioned and connected by long welded rails. Two multi-purpose gantries were used to pull the rails into place, and they were eventually concreted into position using a specialized concreting train that operated every night. Once the tracks were set, they were used for logistical purposes, enabling railroad vehicles to transport materials and equipment through the tunnel. Another critical installation was the overhead line system, which runs along the top of the tunnel, carrying 25,000 volts to power the trains. Alongside this, a walkway was installed running the entire length of each twin-board tunnel, providing access for maintenance and safety. Additional mechanical systems were also installed, including the fire main, a pipe that runs throughout the tunnel and connects to each station, shaft, and portal. 4,000 luminaires were added to provide lighting, and large ventilation systems were installed, featuring 10-ton fans at each station to ensure proper airflow throughout the tunnel. Another vital component of the railway system is the platform screen doors, which are about 200 meters long and fully seal the platform from the tracks. These doors are synchronized with the train doors, opening and closing in unison to ensure passenger safety. After all the systems were installed, they had to be tested and commissioned. The process of tunneling involves a series of steps to ensure the safety and stability of the tunnel structure. A steel mesh is placed against the tunnel walls to provide initial stability. A layer of shotcrete is sprayed onto the tunnel walls to reinforce and protect the rock. It creates a durable surface that prevents rock fragments from falling. Holes are drilled into the rock to accommodate securing anchors that will hold the tunnel structure. These holes must be precisely positioned for optimal support. Steel anchors are inserted into the drilled holes, ensuring additional support for the tunnel. The anchors lock the surrounding rock in place, preventing movement. Holes are drilled strategically into the tunnel face where explosives will be placed for controlled blasting. The placement of these holes is crucial for effective rock fragmentation. The site is secured, and equipment is prepared to safely conduct the blasting operation. All workers are evacuated to a safe distance before detonation. The blasting holes are filled with a specialized two-component explosive for maximum efficiency. This mixture ensures a controlled and powerful explosion. Detonating fuses are connected to the explosive charges to control the timing and sequencing of the blast. Proper timing is key to directing the force of the blast in a specific direction. After the explosion, machinery is used to remove the loose rock and clear the tunnel for further work. This step prepares the tunnel for the next phase of construction.